go. And share screen. All right, so good morning, everyone who successfully managed to sign in today. Again, really sorry about all the problems with the Zoom link, but I hope it works for most of you now. Okay, so we already talked a little about symmetry. Last time we met, we talked a lot about translational symmetry. But of course, there's different forms of symmetry that one can have in a crystal, which we will cover today. So today's lecture will be on symmetry, plane groups, and actually space groups we'll really cover in part 2 when we meet up next week. Okay, so I mean, I'm sure you've come across symmetry and are already familiar with symmetry to some extent already. There's examples of point symmetry in nature, like in a snowflake, we have six-fold rotational symmetry. We can also find examples of translational symmetry in nature. And for some reason, it seems like we think that aliens are obsessed with symmetry as well. With these crop circles, quite often we find some sort of point symmetry. So yeah, I'd also, again, like to give you a moment to think about what sort of symmetry that we find in these images here. And if you have any suggestions, let me know in the chat, or yeah, just speak up maybe is even faster. Any suggestions of what sort of symmetry the first image on the top left has? Inversion symmetry, yeah. That's a good one, inversion symmetry. So actually in 2 dimensions, inversion symmetry and two-fold rotational symmetry can appear similar. So you could say both in this case. In 3 dimensions, of course, inversion symmetry and two-fold rotational symmetry are different, but in 2 dimensions, they can be considered similar. So yeah, that's a good point. How about the second one, the top one in the middle, if you ignore all the people? Mirror symmetry, great. Yeah, there's a mirror plane that goes kind of right through the middle of this image. Similarly with this jellyfish, there's a mirror plane right through the middle, if you ignore the tail end over here. And also on the bottom, we have 6-fold rotational symmetry and 3-fold rotational symmetry here. Great. Okay, so symmetry, what is it? Well, if you look up the definition of symmetry, it's kind of a vague and abstract definition. So officially, an object has symmetry if it's invariant to transformation. So what does that really mean? So if we look at this image of a butterfly, well, one way, like say if you wanted to draw it with a computer software, one way would be to define the color of every single pixel in this image, pixel by pixel, describing if it's dark blue, if it's light blue, if it's white. That could be one way, but there are more efficient ways of describing what we see in this image. So let's say we just look at the left-hand side of the butterfly. Now, in crystallography, we would call this the asymmetric unit. It's the part of the structure that you can kind of repeat with symmetry to get the whole picture later on. So if you take the asymmetric unit, we also need to know where our symmetry elements are, things like mirror planes, rotation axes. So if you have the asymmetric unit, so if you know what each pixel is colored in the unique part of the structure, and if you know where your symmetry elements are, like if you know that the mirror plane is here, then we can produce the right-hand side of the butterfly by just saying, okay, so for this pixel here, just mirror it across here, and then this side has the same color as the opposite side of the mirror. So this way you can save a lot of data, let's say. You only need to know half of the butterfly and where the mirror plane is in order to be able to draw the whole butterfly. So this saves a lot of information. So with symmetry, yeah, you need the asymmetric units, your symmetry elements, and then you can get the whole picture. So why do we bother with symmetry, like, you know, mirror planes and rotation axes and whatnot? I mean, with our previous lecture, we talked about translational symmetry and how you can use, you know, the unit cell to describe a crystal structure. And yes, if you take a unit cell, I mean, that's much more simpler than describing every single atom in the entire crystal. But still, we can further simplify this down. So still, in one unit cell, like, so this is the structure of a zeolite, zeolite A. It has a cubic structure with a unit cell length of 24.61 angstrom. But still, if you were to describe this whole unit cell, it's quite a lot of atoms to have to describe. I think there's about 500 or so atoms in just one unit cell of zeolite A. So even if you were going to describe this crystal just with one unit cell, you still need to find the positions of all, you know, 500 atoms in one unit cell. And 500 is quite a lot, considering a small molecule structure. Maybe for a protein structure, that's nothing. Okay, but if for zeolite A, actually, so even though you have 500 atoms in the unit cell, actually there's only 5 unique atoms, 5 atoms in the asymmetric unit. So that means if you want to solve the structure of zeolite A, if you know the symmetry and the space group, then actually all you need to know are the positions of 5 atoms instead of 500 atoms. So that becomes much, much, much easier. So if you have these 5 atoms, so it's just 1 silicon, 1 aluminum, and 3 oxygen atoms. All of the other atoms in the crystal structure are related by symmetry. It might be rotational symmetry. So in the middle of this cage here, I believe there's 4-fold rotational symmetry. You can rotate, you know, 90 degrees, and this aluminum ends up being here. So all of these aluminum are related by 4-fold rotational symmetry. And there's other forms of symmetry, like perhaps a mirror plane going horizontally, a mirror plane vertically, and then much more. So by identifying what symmetry we have in the crystal structure, it significantly reduces the number of unique atoms in the structure. Okay, so we're going to go through all examples of symmetry operations that we have in 3-dimensional crystal structures. So we've already talked about mirror planes, rotation, axes. Inversion centers was brought up with the crop circle example, and we've already talked about translational symmetry in lecture 2. There's also other examples: glide planes, screw axes, roto-inversions. Roto-inversion is also called improper rotation. So these on the right-hand side are combinations of symmetry operations that we see on the left-hand side. For example, like a glide plane is a combination of a mirror plus translation. But we'll go through these one by one in a moment. Okay, so in crystallography, we often use symbols to describe symmetry operations. So a lowercase m corresponds to a mirror plane. Rotation, usually you'll see an integer between either 1, 2, 3, 4, 6. Not 5. Inversion, sorry, it should be a 1 with a bar over it. That bar came out a little bit small when I'm in presentation mode, but the bar should kind of go over the entire number. So it's bar 1. Roto inversion, again, it's a number like 3, 4, 6, but with a bar over it. So 3 bar, 4 bar, 6 bar. We don't call it -3, -4, -6. It's 3 bar is the correct way of saying it. Other lowercase letters like ABC, NDE correspond to glide planes. And sometimes we see numbers with another number in superscript, so subscript, excuse me. So these are screw axes. And some of these symbols you'll see in the space group names. Okay, so we'll start off with point symmetry. So with point symmetry, this is kind of a subset of these symmetry operations. Now with point symmetry, that symmetry operation will at least have one point that will not be affected by that symmetry operation. So for example, let's start off with the inversion center first. So say you have like a ferrocene complex where you have iron in the middle, and then you have two cyclopentadiene molecules on top and bottom. So this molecule has inversion symmetry. Say, if you look at this carbon atom here, if you go through the inversion center here, then you'll find an equivalent carbon atom on the opposite side. So these two carbon atoms are related by inversion symmetry. So by performing that inversion, the position of the carbon, you can imagine, it moves. Like this carbon, if you invert it, ends up going over here to find the equivalent position. Now, actually, on the inversion center, you have that iron cation. Now, if you invert the iron cation on the inversion center, it ends up, being exactly on itself. You end up with the same coordinates. So the position of the iron doesn't move because it is actually on the inversion point. So this is what is referred to as point symmetry. So there's at least one point that is unaffected by the symmetry operation. In this case, the iron on the inversion center. So the inversion center itself, that's the point that, even if you invert something on it, it's not going to change positions. Similarly, with rotation axes, you'll have an entire line, in this case, going into the page that is unaffected by the rotation. Also with a mirror plane, it's not just one point, but the whole plane itself will be unaffected. So anything outside of the plane, say like on the left-hand side, will be mirrored and end up on the right-hand side. But any point on the plane itself, after mirroring it, it's going to end up, on the same position, the same coordinates. So these are all examples of point symmetry. With rotoinversion, it's a combination of rotation and inversion. And again, that point that you invert the structure around, that's the point that is unaffected. So again, all of these examples, mirrors, rotations, inversions, and rotoinversions, are examples of point symmetry. So let's go through these examples in more detail. And again, the first lecture that you had on the math repetition, I think, is going to be very helpful for today, because we're going to be describing symmetry and symmetry operations using matrices. So we'll be doing matrix multiplications. So the coordinates will be described in a 3x1 matrix, x, y, z. These are the fractional coordinates in your unit cell, say, of your crystal structure. And these symmetry operations we'll be describing using a 3x3 matrix. So I hope everyone's familiar with this matrix multiplication now. So let's say if we want to multiply this 3x3 matrix with a 3x1 matrix, what you would do, again, I hope this is something that Lasse has covered. So then in this case, it'd be -1 times x plus 0 times y plus 0 times z. So all of that, the sum of that will give you -x. Now in the next row, 0 times x plus 1 times y plus 0 times z gives you y. 0 times x plus 0 times y plus 1 times z gives you z. So by multiplying these matrices out, you end up going from the coordinates x, y, z to -x minus y, z. Can anyone guess what symmetry operation this matrix corresponds to? Actually, sorry, I didn't see it, but it's a mirror perpendicular to the x-axis. So if you have a mirror perpendicular to the x-axis, your coordinates for y and z don't change, but your coordinate for x becomes the negative of what you started off with. So I hope you're familiar with this. This is going to come up again in exercises. It wouldn't be surprising if something like this comes up in the exam too. So it's very important that you're comfortable with matrix multiplication, at least by the end of the course. Okay, so yeah, I like to give examples, in 2 dimensions first. So again, later on we'll move on to 3-dimensional examples. So at the moment, let's stick to 2 dimensions. So we have this picture of a butterfly in this 2-dimensional coordinate system. So we just have X and Y at the moment, no Z, since we're not thinking in 3D for this particular example. So let's say we want to get all of the coordinates, the equivalent coordinates on the left-hand side. So say you have any coordinate XY here. So to get the equivalent position opposite the mirror, then this matrix, this 2x2 matrix, will give you the equivalent position across the mirror. So again, this is a mirror that's perpendicular to the x-axis. So that's the mirror plane is parallel to the x-axis, but perpendicular to the x-axis. So yeah, the mirror plane's in the y-axis. So by using this 2x2 matrix, -1, 0, 0, 1, if you multiply it out to xy, then you end up with -xy. So any coordinate here, you find the equivalent position at -xy. Now, in a 3-dimensional example, we have now, x, y, and z as your 3 fractional coordinates, and we need that 3x3 matrix. So again, the mirror is still perpendicular to the x-axis, but it's parallel to both the y-axis and the z-axis. But once again, we end up with, from x, y, z, somewhere on the right-hand side here, the equivalent position would be -x, -y. -x, y, z. Okay, so again, just the same example, but now actually just with the point in space. So say you have some coordinates 4, 2, and 1. If you were to mirror it perpendicular to the x-axis, then that equivalent position would end up being -4, 2, 1. Okay, yeah, just the same example, but in a more kind of 3-dimensionally drawn figure. Okay, so that's mirror symmetry. There's also rotational symmetry, which we've mentioned. So with rotational symmetry, you can have twofold, fourfold, threefold, or sixfold rotational symmetry if you have translational symmetry as well, if you have a unit cell. So this, twofold or fourfold, this integer number, we can kind of represent it and call it n-fold symmetry. So if you have a twofold symmetry, that means you can rotate an object 180 degrees, and then it will end up looking identical to your starting point. So if you want to know, how much you can rotate an object by, if it's twofold, then you take 360 degrees and you divide it by that 2, since it's twofold rotational symmetry, to get 180 degrees. With fourfold symmetry, you can rotate it 90 degrees. So again, 360 degrees divided by 4 gives you 90 degrees. Threefold, you can rotate by 120 degrees, and sixfold, 60 degrees. And again, we're going to be using 3x3 matrices to describe rotational symmetry. So these are the 3x3 matrices for rotations down the x-axis, the y-axis, and the z-axis. So the amount you want to rotate by, you just substitute for theta here. So this involves some cosines and sines here. But say if you want to rotate 90 degrees, down the y-axis, then you can get the 3x3 matrix just by substituting theta for 90 in these 4 positions here. Okay, so let's go through one example or a few examples together. So for rotations down the x-axis, it's this 3x3 matrix here. So again, if you want to rotate by 90 degrees, cosine 90 degrees is 0. So these 2 terms end up being 0. Sine 90 degrees is 1. And then here again, you have minus sine 90 degrees, which is -1. So actually this matrix here, this 1, 0, 0, 0, 0, -1, 0, 1, 0, this corresponds to a rotation of 90 degrees. And similarly for 180 degrees and 270 degrees. So yeah, for special rotations like 90 degrees, 180 degrees, you end up with just a lot of zeros, ones, and minus ones in different positions. Okay, so let's go through another example here, starting off with the same point, say like 4, 2, 1. If you were to rotate this 90 degrees, in this case, down the Z axis, so that's this matrix here, the next equivalent point would be, so if you start off with X, Y, Z, and if you multiply it by this 3 by 3 matrix, you end up with minus Y, X, Z. So I hope if you look at these 3 by 3 matrices with some practice and time, I hope it becomes quite quick. There's a lot of zeros and ones and minus ones. So if I look at this row right away, I know, this is going to give me minus Y, because there's a lot of zeros that disappear in the equation. Again, here you see this row 1, 0, 0. So I know this is going to give me a value of positive X. So if you put this in, so for X, Y, Z, if we say that's 4, 2, 1, then the next equivalent position is going to become minus 2, 4, 1. So X and Y have swapped positions, and then the first position here becomes negative. So we end up with minus 2, 4, and 1. But then we can repeat this. So we can plug in minus 2, 4, 1 as our new values for X, Y, and Z to find the next symmetry equivalent position. So again, the first two terms swap, and then you end up with the negative of the first. Actually, sorry, there's a typo here. It should be minus 4, minus 2, 1. I'm really sorry about that, but there's a mistake here. It should be minus 4, minus 2, 1. And then we can repeat this one more time to get 2, minus 4, 1. Again, sorry for that mistake here. It's minus 4, minus 2, 1. Okay, now moving on to inversion symmetry. So with inversion symmetry, you have a point, and then you invert the whole structure around that point. So let's say you have two tetrahedral molecules and an inversion center in between them. So to say, if you start off with this big circle here, this big atom, you can imagine a vector going from this atom to the inversion center. Now, if you repeat this, so if you go in the same direction, the same amount, the same distance, then you end up on your equivalent point that's related by inversion symmetry. So again, the smaller circle, if you just go from the small circle directly to the inversion center and keep going the same direction, the same amount, you end up at the equivalent point here. So with inversion center, sometimes you'll see a lowercase italicized I to represent it, but more often you'll see a bar 1 to represent that. So again, with this example, 4, 2, 1. So the inversion matrix is going to be minus 1 in all of the diagonal, and you have 0 in all of the other terms. So minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. This is a matrix I hope you can recognize very quickly soon. And so this is the inversion matrix. So the symmetry equivalent inversion point would be minus 4, minus 2, minus 1. And then there's the identity. So the identity matrix is this. You just have positive 1 in the diagonals and 0 everywhere else. So if you perform an identity matrix, nothing happens, nothing changes. You just end up, if you start off with X, Y, Z, you end up with X, Y, Z. So that's quite obvious that if you do nothing, nothing is going to change to your coordinates. But it's good to recognize this. At least mathematically, it's quite a useful thing to know. And also for group theory, you always have the identity, right, as part of the group. Yeah, so why do we have this? Well, sometimes it's quite useful to recognize things. So say we start off with coordinates X, Y, Z, and then we perform this 3 by 3 matrix. Any suggestions what symmetry operation this 3x3 matrix is?
A mirror?
It's a mirror. Perpendicular to which direction?
Why?
Yes, exactly. This is a mirror plane perpendicular to the y-axis. So it's good that I'm glad to hear that you're starting to recognize this already. I guess there was a hint on the bottom here. So if you see just like one minus, if you just see, in the diagonals ones, one or, minus one. And if you see that, yeah, the negative one is kind of in the second position, then, it's a mirror perpendicular to the y-axis. So very good. Okay, so say you perform one mirror, you end up with this new coordinate, x minus yz. Now, if you repeat this, so if you mirror from x minus y minus z, you end up back onto x, y, z. So mathematically, this is really easy to show. If you just multiply these two 3x3 matrices, so if you have your mirror perpendicular to y, and you do another mirror perpendicular to y, and you multiply these matrices out, you see you end up with the identity matrix. So mathematically, we can also show that if you mirror an object twice, you end up back in the original position. Okay, and I think this is the final example of point symmetry that we're going to go through. Improper rotations, also known as roto-inversions. So like I said, this is a combination of a rotation with an inversion. And there's different examples of these. So we're going to start off with the roto-inversion called 4-bar. So like I said, there's going to be a rotation. So what's drawn in pink or magenta is the rotation axis. The green dot is the inversion center. So let's say we're going to start off with a point number 1 here. And let's start by rotating it first. So let's rotate it 90 degrees. It's 4-bar, which means we're going to rotate it 90 degrees. So we rotate it 90 degrees around the rotation axis. So we end up here. But we're not done yet. We still need to invert the structure. So if we invert it from here through the inversion center, we end up at this point here. So this is our symmetry equivalent position. If we start off here, this is the second one. Now we can repeat this. So again, if we rotate 90 degrees and then invert it, we end up on here, point number 3. And then we can repeat this one more time. So if we repeat it, so 90-degree rotation, invert it, we end up on point number 4. Now, if you happen to do this one more time, that's again would be like doing this 4 times is the same as the identity. So if you rotate it 90 degrees and invert it, you end up at the starting point. So again, sorry, this is just describing what I was just talking about a moment ago. So if we repeat this 4 times, we end up with our 4 symmetry equivalent positions related by roto inversion, this 4-bar symmetry. Okay, but we can also have 3-bar and 6-bar. So this is 2 examples of ethane. But one is eclipsed and one is staggered. So with the example 3-bar, let's say we start off with this hydrogen atom first. And our rotation axis is down the carbon-carbon bond. So let's say, let's look at it down the carbon-carbon bond. So if we start off with position 1, it's 3-bar, which means we rotate it 120 degrees first. So we can rotate 120 degrees. So we end up on 2, but we're not done yet. We still need to invert the structure. So once we invert the structure, we end up on point 5, which is on the opposite carbon atom. If we again rotate it 120 degrees and then invert it, we ended up on point 3, and repeat this. So 120 degrees, invert point 4, 120 degrees, invert point 2, and so on and so forth. So you can repeat this to get all 6 hydrogen atoms in the staggered conformation. Now with the 6-bar, it's similar, but now of course we rotate only 60 degrees. So again, we view down the carbon-carbon bond. Starting off with point 1, this hydrogen 1, we rotate it 60 degrees, and then if we invert it, we end up on the hydrogen atom that's hidden behind number 3. So that would be number 4 here. So from 4, if you rotate it 120 degrees, 60 degrees. Sorry, I keep saying incorrect things. If you rotate it 60 degrees and then you invert it, then you end up back, and then you end up on hydrogen number 2. So if you can repeat this, 6 times to get all 6 hydrogen atoms in this eclipsed form.
So you can.
Yes, don't be sorry, but feel free to speak up.
Okay, perfect. So in this example, we always mix a rotation with an inversion.
Yes.
Would it also be allowed to do a rotation with a mirror?
Rotation with a mirror. Oh, good question.
If we take the upper example, which is 3 bar.
Yeah.
If we would rotate it 60 degrees and then mirror it, we get kind of the same.
If you rotate, yeah, you could think of it that way. Wait, let me think. If you rotate it, it's 3 bars, so you want to rotate 120 degrees. So let's say we start off with 1, and then you rotate it 120 degrees, end up on 2, and then you mirror it.
Do that, but rotate it 60 degrees instead.
Yeah, you could rotate it 60 degrees and then mirror it. Yes, then you would end up with, say, like on 6, for example. Say,
yes. Or are that operations that are not,
I guess,
standardized or so?
I've never thought of it this way. One easy way to check. Actually, so I need to think about this. This is a very good thought experiment, or a good thing to think about. But I think the easiest way to check this is actually using the matrix multiplication. So you can multiply these two to see if you end up with the same matrix. So if you combine, the 3 by 3 matrix for the rotation, the 3-fold rotation with the inversion, and then also if you do the same for this 6-fold rotation with the mirror, if you end up with the same matrix in the end for both equations, then they would be identical. But I would need a moment to think about that, if these are actually equivalent. At least in this example, it certainly seems so.
Yeah, and with the 4 bar, it will also work, I think.
With the 4, yeah, I actually need to think about that. Maybe, yeah, that's, thanks. I've never thought about that, but that's interesting. So with the 4 bar, but in this case, you would, let's say, how would you do this? I guess you would still want to rotate 90 degrees, but then, yeah, I guess if you rotate 90 degrees, you end up here. And then if you have a mirror plane here, perpendicular to the rotation axis,
yes,
then you would end up on position 4. Yeah, I think the easiest way to absolutely be certain is to actually do the matrix multiplication to see if those 2 different combinations end up giving you the same matrix in the end. I think that would be the easiest way. That's how I would approach seeing if those 2 ways of thinking would actually be equivalent or not. I might do that after this lecture, just out of my own curiosity. But thanks, that's a really interesting point that you make. But yeah, for the 6 bar, then would you wait? For the 6 bar, you would rotate 120 degrees instead of 60. Yeah, that's certainly might be another way of looking at things. Yeah, I'm gonna look into this right after the lecture. Thanks for that comment. Very interesting thoughts. But certainly what I have presented today, this is the standard form, the standard kind of way we describe the symmetry and often think about it. Although, like we talked about, with unit cells and the Bravais lattices, things have already been standardized. So what we present and teach are the standard forms, but of course, the standard form isn't the only way of doing things. Okay, thanks again for that comment. Okay, so we don't really talk about 2-bar. Why is that? And I think this is going to come across actually what you were just talking about in a moment ago. So 2-bar, if we were to have it, of course we can do it. So say we start off with that point 1. If you rotate it 180 degrees, and then if you were to invert it like you would for a roto inversion, you would end up here. So actually, 2-bar would actually be exactly the same as just a mirror plane perpendicular to that axis here. So actually, a 2-bar is actually the same as a mirror. And so this is what I want to check with the other roto inversions, if they are related to mirror symmetry combined with perhaps some rotation too with these other cases. And also 1-bar. So say like you rotate it 360 degrees and you invert it. It's the same as just inverting it. So 1-bar is the same as, the roto inversion 1-bar is actually the same as an inversion. But this form, this 1-bar, is something that we do use to represent inversion. So for example, the space group P-bar1, it's a very simple space group with an inversion center in it, several inversion centers in it. So bar 1 we actually use to symbolize inversion centers, but I've never seen mirror planes being described as 2-bar roto inversions. But it is the same. Again, this is just this. The mirror is the standardized form that we use. So for those of you who have, are quite familiar with symmetry and spectroscopy, for example, you're probably more familiar with the Schoenflies notation rather than the more crystallographic notation that we'll be talking about in this course. So there are equivalents. So for example, rotations in Schoenflies notation will be like C with some integer subscripts. So that is the same as just, the integers that we have, like, 2-fold rotation, 3-fold rotation, 4-fold rotation, which would be described with just an integer. So a lot of these are actually equivalent to one another. Okay, and I guess this is, I think, the last point I want to make about the point symmetry is that we can divide up the structure into positions that are called general positions and positions that are special positions. So again, going back to this ferrocene complex, all of the carbon and hydrogen atoms are on general positions. So in a general position, say again, we have that inversion center on the iron cation. So, oops, sorry, I'm getting ahead of myself. So with a general position, if you were to perform a symmetry operation, then you generate new coordinates, new positions. So if you start off with this carbon in the back, if you invert it, you end up with this new carbon atom here. So you end up with 2 carbon atoms in the end. But special positions, like I said, these are the positions that give rise to that point symmetry that I was talking about. So say if you start off with the coordinates of the iron cation, and if you were to invert the structure, you end up on the same position. So we call this a special position. So by performing that symmetry operation, we end up on the same place. We haven't generated any new coordinates. So special positions, if you were to perform, these symmetry operations, you end up with fewer equivalent positions as a general position, let's say. Okay, all right. I think now's a decent time to take a break because we're going to be moving away from point symmetry now and going back to talking about symmetries that have some translational components to it. So it's 10:55 according to my watch. Let's take a 10-minute break and resume at 11:05 then. Okay.
Yes, sure. Okay.